Good afternoon, everybody. Thank you for joining this webinar today. The topic for the webinar is design and optimization of axial flux motor for EV and industrial applications using COMSOL Multiphysics. I am Nirmal Paudel. I am the lead engineer at Veryst Engineering. So my background is electrical engineering by degree. So I have worked in the past as an electromagnetic expert for various companies, including COMSOL, ABB, and also was an associate professor in the university for a while, and now at Veryst as a lead engineer, primarily working on the electromagnetic design and optimizations of the devices that involves, multiphysics as well. So I hope if you have any questions, please type it in the Q&A box there, and I will try to address them at the end of the presentation during the Q&A. So also please note that this webinar will be recorded, and those who have registered will get the recording of this webinar. The agenda for today, we'll just briefly introduce what we are at Veryst Engineering, what we do, and jump into the major topic for today onto axial flux motor and how it's been done, or how it can be modeled in COMSOL environment, different study type. I will also demonstrate how the optimization is done, and there will be several case studies, primarily double the stator, single rotor configurations that we'll be analyzing today, and then also a comparison of 2D, 3D results. So if time allows, I'll also open the models in COMSOL and then just demonstrate. All right, so we are a highly technical team of 12 engineers. Our company is located in our headquarters in Needham, near Massachusetts. So what sets us apart is that we have more than 80% of our staff hold PhD. So this reflects the depth of the expertise that we bring to every project. So usually customer comes to us when there is a multidisciplinary type of research or the product development. And we, multiple team members jump into the project to make that happen. Our core strength is basically ability to deliver academic level engineering rigor, but at the speed of industrial demand. So we combine deep theoretical knowledge with practical and timely execution. We also have a 3,000 square foot of mechanical test lab for mechanical testing, and then that can be combined with the numerical simulations as well. So these are the four major pillars or the business practices for us. Material engineering, mechanical testing, material modeling, then multiphysics simulations, and the failure analysis. So we help client choose the right materials for the applications through advanced consulting and material characterization, ensuring the optimal performance under real-world scenarios. And then we perform custom testing and material modeling of complex materials like polymer, adhesive, and foams, especially with the standard ASTM test doesn't apply. Such as for highly nonlinear temperature or pressure sensitive materials that we do a custom testing in-house. So our team brings academic level expertise in solid mechanics, fluid dynamics, thermal analysis, and electromagnetics, coupled to solve complex engineering problem that spans in multiple physical domains. So also we provide a root cause failure analysis for industrial and legal clients, drawing on deep engineering knowledge in the material science, mechanics, and manufacturing to understand what products fail and why it failed. At Veryst, we specialize in solving highly coupled multiphysics problems, often involving complex nonlinear interactions. Later in the talk, I will also walk you through a few real examples to illustrate what our practice areas are. And we are flexible and tool agnostic when it comes to the simulation software. Depending on the problem and the client preferences, we use tools something like Abacus, COMSOL, ANSYS, or Elastina, or other packages, always selecting what best suit the complexity and the physics involved. And we are also certified COMSOL consultant. And I personally led electromagnetic group at COMSOL as an application engineer in the past before. So we bring deep expertise in both physics and the software itself. So here are some of the examples of multiphysics simulations, combining fluid flow, solid mechanics, EM, heat transfer, or chemical reactions. So the example on the top right is a turbulent mixing of mRNA vaccine production. The project involves simulating turbulent flow and mixing of fluids inside a reactor used for mRNA vaccine manufacturing process. We couple fluid dynamics with species transport to optimize how rapidly and uniformly the critical ingredients mix under high shear conditions. And then the one on the bottom left is a combustor liner heat transfer, where we modeled heat transfer in high temperature gas turbine combustor liner. The analysis combined basically the conjugate heat transfer involving hot gas flow and conduction through the liner with thermal stress analysis to evaluate durability and cooling performance. And the cal rod heating, which is a basically electric heating of cal rod. We combine resistive heating element with the thermal simulations, and to understand the thermal behavior during the power input conditions. The one on the bottom is a piezoacoustic particle focusing. We develop a multiphysics model of a microfluidic device where a piezoelectric transducer generate acoustics waves to focus the particles. This requires basically coupling of structural vibration, acoustics, and fluid distribution interactions, all in the microscales. On the top, we have a flexible hot valve. This is a biomedical example involving a soft flexible hot valve under pulsating blood flow. The analysis combine fluid destruction interactions, hyperelastic materials, and transient boundary conditions to predict valve behavior under realistic loading conditions. So each of these cases showcase how we apply advanced simulations across mechanical, thermal, electrical, acoustics, and fluid domain to solve the real-world engineering problems. So these are just a few examples that we can share, but we have done a lot of projects that we can't share because of the customer proprietary information. A little bit about the Veryst Mechanical Test Lab. So we offer a wide range of mechanical testing services with the particular emphasis on plastic, polymer, and adhesive. Our primary focus is on non-standard or a custom testing. We focus closely with each client to understand their goals and design tailored test plan to extract the material behavior most relevant to their application. So here are some of the tests that we do. Quasi-static tension, compression, and shear, fracture toughness, DMA, or we also provide, for clients who need data for simulations, we go beyond testing. We offer a material model calibration and develop a constitutive model that can go directly into the FEA workflow. All right, so now into the topic, axial flux motor. So let's do a brief comparison between what is radial flux motor and a axial flux motor. So in electric motors, magnetic flux that refers to the field line that generate basically either through the permanent magnets or to the current carrying conductors. So the direction of flux relative to the motor rotational axis determine whether it's a radial flux or the axial flux. So on the left-hand side here, we have a radial flux path. So where we have the axis of rotation or the shaft. And on the radial flux path, what we have here is the rotor inside and the stator outside, or vice versa in different configurations. But the idea here is the flux line goes from radially outward, or in other words, perpendicular to the shaft. So that's why it's called a radial flux motors. And these motors are usually in cylindrical in shape and are commonly found in most industrial and automotive applications. Whereas the axial flux machines, what we have here is the flow of flux is parallel to the shaft or the axis of rotation. So as you can see, we have a rotor on the outside, the stator inside, and then another rotor outside. So the flux actually going from rotor to the stator to the rotor, and likewise. So it's always in parallel to the axis of rotation. That's why it's called the axial flux machines. And the design is usually like a disc shape, as you can see here, which will allow for a compact, high torque solutions often used where space and weights are critical, like in EV or drones. And the understanding this difference is crucial when choosing a motor topology for performance or packaging or efficiency optimizations. So, but today, let's look briefly into some of the advantages. Basically, it offers a compact structure, especially short axial sizes, which is ideal for example, in-wheel motor technology for EV. Small stator core volume, therefore reduced both stator core losses, and low weight, obviously because of the compact size, high torque and high power density. And they also offer a flexible and modular structure, as motor can be stacked to increase the torque or the power if needed, as you'll see in some of the configuration in the next slide. So the only disadvantage is that the manufacturing of such an assembly problem due to complicated structure, and there is still ongoing a lot of research going on the manufacturing process. It is it's still in the early stage. And the higher cost, and because of the technology is still in the development. And the other disadvantage is that it's prone to non-uniform air gap due to strong axial magnetic force between the stator and rotor. So it's hard to maintain that constant air gap. And so there is a possibility of more noise and vibration. All right, for today's topic, we'll let's jump into the different topologies and then pick one for further analysis. So axial flux motor can be divided into different topologies, as here, different, author, they may characterize differently, but here I have basically the 4 different ones. Single stator, single rotor, axial flux machine. So we have a single rotor and single stator, they're stacked on top of each as a disc shape. And then the other one is a single stator, but double rotor. So you have a stator in middle with the windings, but we have the rotor on the outside with a magnet ring and a back iron. Same thing on the other side. So it's a 2 rotor, 1 stator in the middle. And just the opposite of this one, where we have the single rotor inside and then a stator, 2 stator outside. So today we'll be discussing or going through this topology a little bit more in detail. Then multi-stator, multi-rotor. So we have here stator, and then we have 3 rotor, 2 outside, 1 in the inside, in the middle. So now there are some advantages for this single stator double rotor configurations because of it's asymmetric, so there is less vibrations. The advantage of this one double stator, that's stator in the outside is that it's, the stator is outside, so is the heat dissipation is easier from the coil, so it's more preferred from the thermal management perspective. And then the multi-stack is basically helpful when you need the high torque, where you can have a number of stator or rotor combined to have more torque. All right, so the application-wise, I think we briefly mentioned that the radial flux motor are mostly used motor architecture today, and we'll find them in traditional electric vehicles or industrial machinery or HVAC systems, where their cylindrical geometry and well-established manufacturing process make them ideal. But axial flux motor, on the other hand, are getting rapid traction in the next generation applications, particularly in electric vehicles, e-mobility solutions, robotics, aerospace, and marine propulsion, where compactness, lower weight, high torque density are the major advantage. And below here we've shown a few examples of commercially available motor for different manufacturers, highlighting the diversity in size, geometry, and form factor. So basically, it's they can range from the voltage level from 700, low range of 580 to 700, but providing a continuous torque of 400 Newton meter. This one is 260, 140, or even this one is just 90. So there are a lot of different variations that can range from the weight perspective, it's 10 kg all the way to 37 kg. And then in terms of the thermal management, there's a water cool or water mixed with air or a combinations of other cooling agent. So these are just a few examples. Now, I think regardless of what topology we use, I think it's the finite element tool like COMSOL could be useful, and that can be used to design and optimize the design configurations, not only the EM, but also the thermal and other aspects. So when we talk about modeling in COMSOL, that can be done in different ways. Starting with the stationary study, basically we basic information like torque and speed. The static response only, usually for the stationary study, you don't typically model the hysteresis in the motor. Then you can include into the time domain where the eddy currents effect or the losses that are coming from the motion, also due to the harmonics, can be captured. It can be a little bit computationally expensive, but this will also provide a torque ripple or Cogning torque, etc. When you have certain speed on the when you solve the time domain study as a function of rotations. And then obviously we wanted to parameterize on geometrical material dimensions and the voltage level or other parameters. So it's always helpful to do the parametric sweep on certain things so that we can, from the large remodeled region, we can narrow down into the few parameters that are more sensitive to the design and focus on the optimizations on those critical parameters later on in the optimization study. So the optimization could be to save the materials or to maximize the device performance, or could also have a cost function to reduce the cost of it. Obviously, the optimizations, you have to run more carefully if you have a single optimization functions or multiple functions. And then finally, you can also combine it with multiphysics simulation. So there is literally, unlimited possibilities of how you can combine this type of studies. All right, let's look into a first example where we have a double stator, a single rotor motor. So here is the geometry of it. So we have a 9-slot per stator, and then 10 rotor magnets. So the pole pairs numbers is 5, and then these are the dimensions where outer diameter is 300 millimeter, and there is an air gap of 1.25 mm, and there is a permanent magnet with a thickness of 4.5 mm, and then there is an angle definition for a permanent magnet where there is a gap between the magnets, and it's only covered 28.8 degrees. So the initial dimensions that we picked is from this reference here. So what we have here is we have a rotor in between with the permanent magnets, and we have a stator on the bottom, and on the top where there is a back iron with stator tooth and coils, three-phase coils. So what we did is instead of solving this like a 3D, the idea here is basically you slice it at certain radius. So the first initial model that we have here is kind of average radius of this one. So we are somewhere in the middle. We did a insertion. So that is the radius we capture, and then kind of unfold this motor so that it looks like the machine here on the flat, like a linear motor. So, and then you can see the windings here, A, B, C, on the top and bottom. And there is a rotor, which is kind of sandwiched in between those two with this smaller air gap between them. So this is one way to start with. So what we do is basically just pick the average radius and kind of unfold this geometry and convert that into more like a linear motor, and assign all the physics, basically all the windings configurations, the material assignments onto the rotors, into the magnet basically, and then also on the stator side. So if you want to model this as a linear materials or the BH curve or the full hysteresis, you can only choose that within the software. But here, I think we're doing only the BH curve for the materials. Now, what we did is we performed the 2D analysis of the motor, and this is the half symmetry. So we only solved the top half of it so that we can save the time and the resources. So what we apply is the periodic boundary condition on the ends here. So it's a continuity on either side. And then also we applied basically archaeotorque method, so which is more into a, less sensitive to the mesh size, unlike the maxwell stress tensor method, where we calculate the torque on the volumetric or the domain level feature. So instead of using a rotating machinery, in this particular example, we use magnetic field interface actually. And this is just a mapping of the results on the second half using a data set in COMSOL, where you can just mirror the image of the data on the top and to the bottom. So it's the result for the full model. So this is what we did just for one slice. And now we have the results of the torque that we obtained from the mid sections, or the mean radius is like 280 Newton meter. So then what we did is we also performed the simulations, a bunch of simulations starting from like the innermost 75 to 150, which is the outer radius, and calculate the torque for each of them. So pretty much we have 9 slices here with the simulations, and what we found is we then calculated the average of this torque here. So from the model setup, if we just set up the model properly, it's just the change in the radius, nothing else. So all the assignments and the materials into the model are intact. So you can just change the radius of the magnet incision where you're taking it. So it actually just increase the length of the motor, and accordingly everything is scaled up. So then you can perform the simulations in one go and calculate the average torque from all of them. So then the average is 267.33. So now what we want to do is compare our results from the 2D analysis, or the combination of the 2D slices, and compare it with the 3D model. So then what we did is we set up a 3D model, again, a half sector of it, only at the top, not the bottom. So then we perform a transient simulations for the same, and what we found, this is the time domain study, so usually the initial, the oscillations here, but I think this final will be settling to about average 256 Newton a meter. So this is very close to what we found on the 2D analysis with the multiple incision simulation circuits, up to 67. So then here on the left-hand side, the image is showing the magnetic flux density and the current density in the coils as well. So the current density is about 7.76 amps per millimeter square. The magnetic flux density is 2.46 Tesla. Now, once we have the initial design, then we would like to also optimize some of the parameters on the machines. So optimizing the same in 3D is will be computationally very expensive. So the idea here is we want to do the optimization now. Once we know that the 2D, 3D are sort of in the same range or very close. So the idea here is to optimize the design in 2D and then test that in the 3D. So what we have here is we set up the optimizations with the 5 parameters. So the parameter 1 here basically have the chamfer radius, and 2 is the magnet thickness. Third is this is the tooth head height, and then 4th is the tooth width, basically this one here. And then 5 is the stator iron thickness. So we want to also vary the thickness of the iron in the stator. And this is the initial design on the top, and the bottom or the middle one here is the optimized design. What we see here is some of the change. A little bit zoom into this one where the optimized design, we have this parameter A is increased, and 2 is increased, 4 is decreased, and 3 is also decreased. So in the tabular form, what we can see here is the chamfer radius, the optimized value goes up. Magnet thickness also goes up. So it is obvious that you're putting more magnet into this theta, but I think there was a saturations on it. So I think it's increasing the thickness is needed for torque optimization. Then tooth head thickness actually decreases. Tooth, they want the optimal design recommend to be less. Similar tooth head width is also decreased. And then now that stator iron thickness has gone up slightly. So here is the actual torque as number of iterations. So it went to 320. Now, so we basically after optimization we increased from 280 Newton meter to 320. That's quite a change between the two. So here is a graphical comparison: the initial design, the blue, and the optimal design, the green one. So the other example is that, okay, we have a single or double stator design, and we also perform the optimizations on that configurations. But what can we do with the 2 stator? Can we just reposition them in different ways so that we can, get more torque out of it? So rather than adding any other, other stack or some other, optimization. So the idea here is just rotate one of the stator on different directions and making that offset and see if we can increase the torque. So the idea here is pretty much the same configurations, but only difference is that we rotate the bottom stator by pi degree, basically, 180 degree. So then almost everything is same, and then now we perform the simulations on it and compare the results with the previous one. So the top one is basically without offset. So the earlier simulations that I talked, so we have, all phase A, the tooth pole are also matching. They're perfectly aligned on top of each other. So there is no offset or asymmetry. But on the bottom one, you see that it is rotated by pi. So your B phase, B plus plus, for example, is here, which is now the starting below the A plus phase here. So it's rotated by pi degree. So and then also the tooth are offset. They're kind of one mid place is in the gap, and those meet in another gap. So it's kind of alternate design. So the idea here is, we want to capture or have a more flux on the air gap at a time, so that we generate more torque. So this is the initial design on the top, and there is the optimal design. So pretty much we did the same thing as we did for the earlier design, and performed the optimization with those 5 parameters. And what we saw is, for this design, just the offsetting it, we got 359 Newton meter. And then after optimization, that even goes up to 404 Newton meter. So there's quite an increase in the torque after that design. So here on the design side, what we have here is again the same parameters. So this is the initial design, and then the optimal design. So now in this case, chamfer radius actually has decreased, and earlier it was increased. So the actually the optimized values for the initial kind of symmetric design and the offset design are different. So magnet thickness actually has gone down. So we're reducing the magnet now. But tooth head thickness. So now this part is going up, and then tooth head width. So the width of this one is the overlapping width. Actually, it's becoming shorter. Like as you can see here, it's getting taller but shorter. Now, the stator iron thickness has gone up just to 1.5, about 1.5 millimeter thick. Here in the earlier one, we had the stator iron actually, the optimal design went almost 5 millimeter thick, which is too much. So the second one actually is better. So we're more torque, but also the thickness of the design on the stator iron thickness increased slightly, not much. And then reducing the magnet size too. So how it compared with the previous one then is, so we have 360 just by offsetting it, and then now we push that onto 404 Newton meter after optimization. So if you compare it with the very initial design, it's 280 Newton, now going to 404. There's quite an increase on the torque. Now there's also a decrease in the ripple. The torque ripple, as you can see, the ripple here is large, whereas the torque ripple on this one is smaller. This is the same idea here. We have the results where we slice this offset design and simulate it for 9 different slices. And then what we have here is basically, comparison for different radius. So if the radius is smaller, your motor in the a linear fashion will be smaller. But when it's the out radius, it's getting longer. But once you have the model set up correctly, you should be able to just run, a few more iterations. That should change and automatically compute the torque for each of them. So what we found is the average torque is like 384 Newton meter. This is before the optimization. And then after optimization, so we did 404, as I mentioned. So any questions? If you have any questions, please use the chat. So I will monitor the chat and try to answer them at the Q&A. All right, so So this is what I have here so far in the comparison of the torque. We also, extended this to the real world scenario for our clients, comparing this with the 3D model after optimizations, and that matches within a few percentage of accuracy. And also we work on some kind of thermal design on the configurations. That's being proprietary, we can't say, but this is the basic idea of starting, on the design process. All right, so I think it would be good to also look at the software here and see how it's been done. So we have basically this is the COMSOL window. So we have a model builder on the left, settings window, graphics on here, and we have a bunch of buttons on the top as in the ribbon. So you can always go and work from, from definition, geometry, material, from the left to right in the ribbon, or from top to bottom on the model builder. So here, so far, we have parameters defined for, stator, rotor, and then also we have parameter for coil configurations, speed, and symmetry factor, and likewise. So we have assigned a current input as a variable with different angles, opposite angle by 120-degree out of phase. Then, so we have different selections just for, modeling ease. So what we have here is the identity pair, which is generated after finishing the geometry. There are two parts, basically. We have the stator and the rotor. So we have a union of two parts, and we form a assembly between the two. So the identity pair is that's separate between the stationary part on the top and the rotor on the bottom. So always remember that you have to finish the geometry with the two unions, and the air gap between them, between the stator rotor, has to be divided. We have the materials here, soft iron, and then we have a magnet, and we have the copper for the winding. And we have a moving mesh, the moving body, which has, we're solving the linear fashion, so we convert the rotational speed into linear and put it as a function of time here. On the magnetic field physics, so what we have so far is basically we have a periodic conditions applied on this one, which is a continuity on this end and also in this end. And we apply a periodic condition for the moving part. Same thing on the other side. So what we have here is the magnetic still. We're applying the BS curve on it. So the BS curve. This is what we use. This is also from COMSOL library. And we have a phase windings. This one, phase A, B, C. Obviously, we have to have a reverse current on some of the winding, half of those windings. Then on the magnet side, it is a linear pattern with north and south. So it's kind of repeating over. And then we apply a perfect conductor, which is a symmetry on the bottom. And then the force calculations. So here's the mesh. We have different sizes assigned on the boundary where the periodic condition is applied. We first mesh on the edge on the identity pair on either side. And then what we did is on those periodic boundary condition, we apply the identity mesh on either side. So finally, free triangular everywhere. This is our mesh. Sorry, I'm going a little bit quicker here because of the time. We have 5 more minutes before the Q&A. So what we did is first we have we want to know what is the best position of the rotor stator so that we get a maximum torque. That's kind of initial angle. And once you have that initial angle, then you perform a simulations where you have a stationary. The reason for stationary is because we have a magnet, permanent magnet. So once we have permanent magnet, we have to set up a study so that there is already a magnetic field, a static magnetic field from the magnets coming. It's unlike the coil where it's turned on and off. So we will not have the magnets on and off like that, right side. So we always have to have a stationary study followed by the time-dependent study, where time-dependent basically is applying to the motion here, which is a function of time, but also a function which is a current here, which is a function of time. We have the frequency times. Then, so once you pretty much that's what you solve. These are the and then this I pretty much have all the studies done in one model file just for demonstration here. So this one is after optimization. So basically, I performed the optimization. I picked the updated parameters, 5 parameters, and updated on the geometry sections, and then run the after optimizations on the same one. But for optimization, we optimize the torque, and then basically it's the maximization of torque, and then we have a parameters with initial values and then limits, upper lower limits for each of them. So now these limits are determined by sometime manufacturability or sometime by the constraint that you have on our design limits, right? Sometimes there is a limit, hard limit from the customers or from your engineering team that this cannot be thicker than this or smaller than this. Same thing for manufacturability. There's a limit. So you have to be very careful on selecting these bounds, upper lower bounds on optimization. So that's pretty much so on the result side. Let's see. All right, so these are the results. You can extend the results for the other sector as well, if it's a linear motor, but this one doesn't have to be. Looks like there's some of the results are cleared. So the other one I would like to open here is with the upset one, where we have both sides up and down. They're offset, so you can't really do a mirror image on this one, so you have to solve both the stator. So here, pretty much the same idea, nothing different. So we have phase A. We assign a separate phase A on the bottom as well. I mean, you can actually combine them if you want, but these were separate windings, so we treated them as a separate. So very similar idea, current angle sweep, and then we did a transient study, followed basically for transient study, stationary first, and then followed by time-dependent studies. And then optimization done on the same 4 parameters, because we found those to be more sensitive from the parametric sweep study on the initial design. I think there are some results comparison. All right, here. So these are, so as you can see, these are kind of the parametric sweep study done. Sorry, the optimization done. So the initial one is before the parameterization, and then we pick the optimal design. The last one is the optimal design, final design one. So there is a comparison between the two from the optimization results. As you can see, the tooth getting shorter, but the height getting increased, and the magnet thickness decrease, and likewise. So you can clearly see the difference on those design. And obviously that can be more quantified in terms of the torque, which is what we are interested in at the end. But this is our torque. All right, we are exactly on time, like 12:45 or 1:45 Eastern time. So let's look into the questions if there are any. I think this is the same workflow that I mentioned during these. Basically, you choose the space dimension. You can do if you always have to see if you can do explore the symmetry on the modeling. For example, you saw that on 3D and also in the 2D symmetric one, I did have symmetry model. There's a material assignment which can be linear or nonlinear. As we saw, BH curve is nonlinear, which you assign. There's also a lot we can do on lamination side, which I haven't done on this one particularly. I think I did in 3D, but not on the 2D. Then on the coil side, it's currently a homogenized coil, but if you have windings that need to be explicitly modeled, you can also do the stranded wires. And permanent magnet, the one that I'm using here is kind of linear, but if you have a temperature dependent property of the permanent magnet, that can be included as a function of time as well. So you can either rely on automatic meshing or customized mesh as I did earlier. So again, there are different study types. You have to always start with this stationary and then move on to the transient or optimizations or parametric sweep if needed. All right, on the design tip side, so I mean, we have to choose the right topology for anything, you know, whether it's single rotors or single stator or something different. And you know, basically we have to optimize the air gap. The smaller the air gap, the better the flux coupling between the stator and the rotor, so more torque. So, but we have to make sure that there is that's possible to maintain even during the harsh environmental conditions. Also the other idea is leverage high aspect ratio windings, because if you have a flat windings that perform better, because you know that's how the flux goes from rotor to the stator in these configurations. As you saw earlier, you know, just offsetting or slot skewing will reduce a lot of things like cogging or torque ripple, but also we saw that it's actually aiding the total torque, which is excellent. You know, you don't have to add extra materials, rather you just position them differently. Thermal management must be a priority. Again, that is a very different topic, but it's something that you have to be mindful even during the EM design. Again, the design can be enhanced from the concept through the prototyping using the FEA tools, starting with the 2D or 3D. You can always integrate that into the mechanical design as well, you know, to calculate the forces on it. If there is any structural, you know, issues that you can mitigate early on. So again, try to minimize the losses through the laminations or having a short windings or optimization of the winding size is critical on the design. So again, there is a lot you can do on the FEA. So it's always helpful to be to use the tool in the right way. I think that is pretty much for the talk. In summary, what we saw here is we saw the modeling workflow of axial flux motor in COMSOL. We compared the torque between different configurations, and what we also demonstrated that the torque comparison between 2D and 3D, and optimization of 2D, so that we don't have to do a optimization in 3D. And we also just share some of the design tips. So that is pretty much for today. And let's look into the Q&A. Just give me a minute here. I'll scan through. Yeah, thank you. There are some suggestions about, exploring the cognitive torque for DSSR example, which we have done it for slightly different configurations for the client. So we're able to actually just reduce the ripple torque pretty significantly with the offset and optimization of the tooth. Uh, so yes, that's very critical, and the software actually help a lot on that. Even we introduced some of the fillet on some of the sharp edges, and that reduced significantly. There is another questions. Were these simulations model verify against the experimental results? Um, uh, if yes, does 2D model or the 3D model represent the overall system from the thermal and electrical perspective better? So what we did is, the experimental model were kind of tested from the client side, not exactly for this one, but slightly different variations after we, improved the design. They were tested, and I would say, obviously, the 3D models were very close to the experimental results, but to get to the 3D, the right 3D, we rely on a 2D model heavily, so that way we could speed up the process. There is another question about on the double stator demo for the offset. Was the offset angle kind of optimized too? Yes. So for this one, actually, pi was the angle that performed the best. Um, uh, okay, the geometry view of the double stator, there were number level. Oh, so actually, in the number level is the automatically done in COMSOL. So actually, if you go to view, there is a way you can actually enable or disable uh, whether you want to see the geometry level, and that will actually be very, very helpful, especially when you're doing with bunch of domains. Having the numbering is much easier. So it's actually a built-in feature of COMSOL. Is automatically generate. I can change those. Uh, so there is also questions about. I'd like to know how to generate current or the voltage waveform for a switch reluctance motor in COMSOL. The waveform per current required for a switch reluctance motor is completely different from that of synchronous motor. Uh, I would say that generating the voltage current waveform should be same as long as you assign them as a coil feature, whether it's stranded or multi-turn coil. The post-processing variable available as a current or the voltage. There is also a variable available for the induced voltage in case of generator, for example. So it should be pretty trivial. So I would suggest that you look at some of the examples in the model library where there is the current voltage waveform plot, unless I understood differently. But I think that's as examples in the model library should be helpful. All right, that's pretty much the questions that I have seen here, unless you have any other questions. So I think it's time to close, I guess. All right, thank you everyone for joining this webinar, and I hope it was helpful. And I wish you all the best in modeling. And if you have any questions or concerns,